Cloud. Okay. So starting for a bit of statistics, and then we will talk about course requirements. Okay. So when you think about statistics, everything shared, you can see my screen, right? All good? Yeah, okay. So when you think about statistics, first kind of idea is various polls, surveys, experiments, and it's pretty correct idea of what statistics is all about. So we're obtaining data, but then we also want to analyze it. Statistics is, of course, the main topic is to analyze the data, not just to collect. And has become really ubiquitous, not just in the recent years, but in the last decades, really, 30, 40 years. So businesses collect enormous amount of data, and it's not just Google and Amazon collecting, trillions of gigabytes. It's your corner store is also collecting information if you have some kind of gift card from them or some kind of card from them. We're also collecting the data on you to see what you buy, what should we advertise to you. So this is all very much relevant, and all the companies, all the medical facilities, they all collect enormous amounts of data, and this data needs to be analyzed. So statistics is really these days at the forefront of pretty much every science, not to mention good old engineering, etc., which always use statistics. But say even psychologists, you may find it surprising, say I'm publishing papers recently with our psychology professors. So they actually need a lot of statistical analysis. You think of psychology, usually it's more for kind of social science, humanities, not math. But it actually uses a lot of statistics and complicated statistics, a lot harder than even you study in undergrad. It's like graduate level statistics. So let's start with kind of business medicine example. So let's say a new cholesterol drug is developed, which is supposed to reduce cholesterol, and the decision needs to be made by management if this drug is worth pursuing. So they create a random sample of 200 volunteers. And whenever such studies are done, you always want to have two groups: treatment group, which is going to get a new drug, and control group, which is going to get either old drug if it exists, or so-called placebo if no old drug, so that people get something looking like a drug, but it's really nothing there, okay? And so say 98 patients, so you randomize 200 volunteers into 98 patients in treatment group and 1 or 2 in the control group, okay? So let's say after a month, so we see that 64 out of 98 in the treatment group had more than 10-point reduction in cholesterol level, while in the standard drug group, 78 out of 102, or over 76%, had such a reduction. So we see kind of perhaps surprising result as well. We were hoping that new drug is doing better, but in fact it's doing worse, okay? So that underlines, by the way, the importance of so-called two-sided testing. Not only you want to allow the option for this to go new drug better than the old one, but also vice versa, okay? But a more important question is really, is this difference statistically significant, or it's just random variation? Remember that this is data. It's not always same. It's always different. There's always variation. So even if you have a perfectly fair coin and you flip it 100 times, it's not going to come 50-50, right? It's going to come something maybe not too far from 50, but still not 50. And each time it's going to be different. There is sort of natural variation in the data. So let's say, for the sake of argument, that when new drug came 5%, say, better than the old one. Is this random variation, or is it really an improvement? Is it statistically significant? And that's really the main question of statistics. We're not ready to answer it yet, especially for this type of problem, comparing two proportions. That's the end of chapter 5. There is quite a bit of time and development we need to go through to be able to solve such a problem completely. But that's the main question of statistics. What's random variation and what's more likely to be real effect? Okay. So any questions so far? Oops. No. Okay. So next we want to talk a bit about data. So data has to be collected and organized in very neat and precise form. Otherwise, statistical software is unable to deal with it. Okay. So here's a good example, and this is one of a file which we're actually going to use a lot in this book. It's help RCT file. It's much bigger, of course, when I'm showing. Here there are 453 people randomly selected from facilities which treat people with abuse problems, substance abuse. Okay. And for each person is a row. So it has this data frame or data matrix structure. Each row case is a patient, and each column is a variable. And that has to be the structure. Okay. So Excel is actually, it looks a little bit maybe like Excel, but Excel can do all kinds of other things. In Excel, you can have like one chunk of the data in one place and another chunk, and another chunk in another place. Well, no, not for statistical data. It has to be clean like this. And there should be also no computations inside file. Like in Excel, you put like little computations here and there along the way. Well, no, not for statistics data set. Only data and only in this clean format, nothing else. Okay. So it's important to also look at this data and understand the difference between different variables. So we have numerical or so-called quantitative variables, which are numbers. In this case, it's age. So-called CSD is a depression score. MCS is a mental capacity score. PCS is physical health score. So these are all numerical. But homeless, sex, and substance are so-called categorical, qualitative variables. They are not numbers, they are labels. Okay, so these are two different kinds of variables. And say this is economics, business economics data set, which we will also use CPS 85. So that's the data on hourly workers' wages. So we have hourly rates here, age, education, and experience in years are numerical variables, while race, sex, and sector, married or single, South, etc., they are categorical variables. Okay. So any questions so far? No. So another file which we will use also is a man health data file. So that has all numerical variables, actually just measurements of age, height, weight, etc. Okay, all numerical. So there is a further subdivision which needs to be made. So among numerical variables, we subdivide them into discrete and continuous. So discrete variables are the counting variables. Okay, you count cars in like sales, people may want to know how many cars are available in some, say, warehouse. So you count for cars. You count students in class. You count, say, production line, how many items they produce. Okay. So these are all discrete items. They have to be whole integer numbers, 0, 1, 2, 3, etc. Okay. On the other hand, continuous variables are variables which take values in some range, any value, like measurements, height, weight, electric current, and any other measurements you make, that would be continuous. One may ask, what if you decide to measure, say, height as a whole number of inches or weight as a whole number of pounds? Does it make it a discrete variable? The answer is no, not really, because you're just rounding really. It's still, if you measure more precisely, it's really a continuous variable. It can still take any value in some range, some reasonable range. Discrete is really counting. When it's discrete, it's only whole numbers. And nominal and qualitative categorical variables could be further subdivided into nominal and ordinal. So nominal are just labels, the gender, car manufacturer, car color, say country of origin, whatever is just labels without any order, that would be just nominal variable. But there are also variables which are labels which do have order, so-called ordinal variables. Say business example would be a very common Likert scale, which many businesses make you fill out. Agree, strongly agree, disagree, strongly disagree, etc. They are labels, but they do have order. And another classical example is, say, military rank. Soldier, major, general, etc. They're all labels, but there is very clear order to them, right? Your standing as a student, freshman, sophomore, junior, senior, etc. So this is all labels, but they have order to them, okay? So notice that for numerical variables, it makes sense to add, subtract, perhaps transform the logarithm function. That in financial applications, they do a lot of so-called log normal functions. So they apply log to something which is very distributed a lot. We will talk about like highly skewed to the right. We oftentimes apply log to it, and that becomes much kind of better normally distributed, say, variable. They do it in finance a lot. So, but this is only makes sense for numerical variables, all these transformations and also computing averages, etc. That can only be done to numerical variables. Categorical variables, you can pretty much just count how many, say, you have sales for cars and you have a warehouse. So you have, I don't know, 300 yellow Fords and 200 red Fords and 400 blue Fords. So color you can just count, there is nothing else you can do with it, okay? You have to be also careful that not every number variable is numerical. Classical example is zip code. Say zip codes are numbers, but they're really not numbers. They're really just labels for areas. You cannot find, say, what's the average zip code of students in this class. Makes no sense, really. Or like numbers on athletes' t-shirts. They are just labels, really. You cannot do any numerical computations for such numbers, okay? So in addition, once you have more than one variable, you may want to consider if there is a relationship between these variables. So specifically, say, if you are dealing with two numerical variables, the best tool to see if there is relationship or not is a scatter plot. So we'll discuss later how you get the scatter plot. But say for those substance abusers, we have CSD variable and MCS variable, okay? And if you plot them together, you see that there is a negative trend. Higher the mental score, lower the depression. Kind of makes sense. So this is negatively associated variable, okay? You always notice, you always put X horizontal variable is always called explanatory, independent, or predictor variable, while vertical y variable is your response or dependent variable. Okay. So I guess by now we're sure everybody arrived. Let's actually talk a bit about course requirements. Okay. So now we don't yet obviously have a Canvas page, but we don't need it too much. Let me grab something from another class. Let me see. Where would this be? Yeah, okay, well, is it? Okay, yeah, that's one. That's the one, yeah. Okay, so, okay, yeah. Okay, so I'm going to send this to Jenny, right? Could you create an email to everybody and also include me on CC so that I have all your emails, ladies? For now, we're going to communicate via emails. So I am writing to Jenny. Okay. And resend it to our girls and to me as well. Okay. So basically, it's sort of general information. That's my email for everybody. That's best way to get to me. But Gmail, not the Tura email. This one I check all the time. Tura email I check occasionally. So now, the course materials are going to be on this website. Why not on Canvas? Because frankly, Canvas is dumb. Canvas cannot do much math and no statistics at all. And this MyOpenMath is an amazing free website which can do like randomized math problems, randomized statistics problems. It can do really amazing, amazing things. Okay, so that's what we're going to work with. So first, you just need to click to create a new account for yourself. And then you click on enroll a new class and provide this information. Okay. And that will get you into the class. And that's, by the way, my Zoom always. Okay. So yeah. So try maybe to create an account for yourself right away. Let me know if there are any trouble with you. We can do it right away because that's you are on computers, right? So
I'm having Wi-Fi issues right now, so I can't.
sorry?
I'm having Wi-Fi issues right now, so I'm on
Uh-huh.
my.
Okay, well, it's okay. No problem. You can create it later. So once so what's that? Sure. Anyway, so once you get in, you will see this. Okay. So it's general welcome. Again, my email to use. Okay. So now I taught various statistics courses many times. And we've done it in many different ways. And for quite a few years, we were doing it with calculators and a bit of Excel. But I've always felt kind of bad about this because you are learning useless skills, really. Nobody does statistics with calculator, and Excel is great, but not for statistics. Excel is great for business, for some modeling, it could be used quite effectively, but not so much for statistics. No. Okay. So eventually I've done two things. I wrote my own book, and you get linked to this book here. So that has been finished only in the beginning of summer. I tried it already once on one group of students, and it went really well. It was good small group of 2 girls in summer, and one got A, another got A+. So that went well. Hopefully it will be the same for you ladies, right? So, okay. And so there is a book. Now, the videos I'm going to be updating, there have been some changes. So I am recording video now, and I plan to update the video. So this will be updated. Okay, there are exam prep already, so that's all fine. So what is the right tool to do statistics? And especially for business applications, you need some good tools. But I wouldn't say it's just business. Like, say, any kind of data analysis has to be done with software. So what kind of software is available? Well, there is SPSS, by the way, but it costs quite a bit of money, and also it can only deal with data files. It will not help you to do kind of computation part of the course. It can only deal with real data sets. And on the other hand, there is a free program called R, which can do everything. It can deal with data sets, but you can also write like little commands to do anything you need. Say, if you need to do mean of a data, surprise, surprise, there is a command mean. You need to do median, there is a command median. I even wrote it in big letters here. Please do not be scared. It's not programming. It's not some kind of big project you have to learn. And a huge advantage, in addition to learning something which is actually useful and you can put on your resume, by the way, that's a good thing to put on your resume that you know some R. But from practical point of view, just as a student, many of the problems in the later part of the course are kind of computation heavy. It would take maybe 15, 20 minutes to do one problem. But on R, you can do the same thing in fraction of a second, and without any kind of small rounding errors or anything. It just does everything with 16 digits accuracy. And it's a huge help. In addition to learning something useful, it's also like, you'd rather do a problem in fraction of a second than in 15, 20 minutes, plus a good chance you get something wrong on the way or copy some digit wrong to paper and back to calculator. And that's a lot of hassle. And so it's much better to learn R. Okay, please do not drop this course, because I hope you're not scared of computers, right? You're okay with it, okay? So there is a way to still do it with a calculator. If somebody really insists, I can personally show you, but I wouldn't recommend it. Let's put it this way, okay? So how do you get R? So there are 2 ways. Now, any of you ladies are on Mac, actually. That's what I wanted also to find out. Are you all on Windows? Then it's much easier, because on Mac there is, of course, a version for Mac, but it's harder to install. But for Windows, it's a rather straightforward process. So I have with step 1A and step 1B. Step 1A, you go here, click on this link. That gets you to basic R page. You click on download R for Windows, and then click on base and just download whatever is on top here, okay? So I even included like few steps here. So download R for Windows, base, and then just download. And very important, well, question. Oh, Chromebook. No, it would not work on Chromebook, but then you will use second alternative. There is a RStudio Cloud. I have a short, like maybe 7-9 minutes video here, how to install it, how to get free account on cloud and use it on RStudio Cloud. Okay, so that's also gonna work just fine. In fact, some students even preferred, even the ones who downloaded R decided that this is actually easier and it's available from anywhere because you're on cloud. Okay, so whichever way would work. This, I mean, it's a short video I made how to do it, so don't worry, it's not hard to get it going. But if you're installing, you first go to here, but beware, this once the download finishes, that's not the end of it. You have to go to downloads on your computer. So where are the downloads? Here. You have to go to downloads and double click on what you downloaded so that it installs it. It's going to ask you for some options. Just keep clicking OK, OK, OK. All the base options are perfectly fine. Okay. So in principle, we could stop here. This is already very usable and nice. But there is even better, like a program called RStudio on top. Once you install, first you install base R. And when there is a program on top of it called RStudio, which you also download and install much the same way, that's also free, of course, everything free. So download RStudio for Windows and install. Okay, and once you do, you will get kind of a nice environment, looking kind of like this. But this, of course, already has some of my codes and such. This you will need to load. I'll show you how step by step once we get there. You get this environment where you can compute. Just to give you an example, say this is the set of data. You call x equal to c parentheses, and you give you data. And then you just find the mean command, find standard deviation for this d command, find median with median command. You just select what you need, click run, and down here you have all the answers. So it's really not hard, and all the commands I provide. And of course, needless to say, all exams and all homeworks are open book, open R, so you don't memorize any of these commands. You just copy paste. I don't memorize many of the commands. I copy and paste. So it's not a memorization, some class in any way. You just have to know what to do. Okay. So once you create R, I'll show you. I have this directory, my R files directory. So I have a file for each chapter. And then for all the homeworks, I also created for you helpful kind of files how to do the homework as well. So it's all there. We will go step by step, and hopefully it will be not too hard. I really hope that the other class and some kind of liked this way. Okay, from my book. So 35% of your grade comes from exam 1, 45% from exam 2, homework 20%, and extra credit project using R. I mean, it would be nice if you actually do it, I would say. So I will find some good file with business and economics data for you. And I think you should actually do it, okay? For the other class before in summer, it was summer too fast, so I did not force them into doing project. But I would say for our class with time left, I think it would be good if you actually do it. I can still count it as extra credit, but I would really encourage you to do it. But no, that's late. So the homework is right here, okay? So each homework problem can be done 3 times at least, and I can add more trials if you need, okay? So say you just click and say, this is my, say, teacher preview. So that's, by the way, like first problem with treatment control, you want to see percentage, 13 out of 59, say, in a treatment group were pain-free due to some treatment we discuss here, and 2 out of 29 in control group. So that's really similar to what we started talking about today, right, with new cholesterol drug trials. And that would be similar whether or not with acupuncture treatment actually helps and works. So if they say propose you to open acupuncture center, well, you might want to know if it's bogus actually or helps. Or maybe like, I don't want to diss all acupuncturists, but maybe like particular ones which are going to work in your center, you want to make sure that they're actually helping people before you invest. So have to run something like this. And they ask you what % patient in treatment groups, what % of treatment in control group. Does there seem to be an effective treatment? But do the data provide convincing evidence that real pain reduction is happening? Well, here you have to be more careful. Without like exact analysis in chapter 5, frankly, this is not a convincing evidence of anything. So even if percentages turn out to be quite different, it's still, iffy thing to make conclusion right away, even the way it look quite different. So be careful, okay? So that's first homework problem. Then there is kind of similar, what are the cases, what are variables based on file description? Remember, we were just talking about this. What's main research question, etc. So yeah, that's the kind of thing we're trying to see. When there is a file here and they ask you, what's a variable, what's an observation, how many participants in a survey, etc. So that's all the things you see from this file, okay? So homework is quite similar, of course, to what we've been doing today, right? Okay, so any organizational questions?
Do you know, like this course, I understand that the work isn't being done on Canvas, but is the like syllabus or anything going to be on Canvas? Or links
We
to
don't
the
really do much on Canvas, everything here on my open math, because Canvas cannot really do much with math or statistics.
right, but do you have like a link to my math or anything like that?
Well, I sent you email. Honey, did you send email to everybody? That should include the.
Is my microphone working now?
Now it's not working. Yes.
Oh, it's working. Okay. So yeah, if you guys want to text me your email addresses, I'll forward it to you. I also forwarded it to you by text, by WhatsApp. But I'll also send it by email so we all have each
Okay.
other's
Yeah.
email
Yeah.
addresses.
So, and honey, could you also send me all your ladies' emails? Okay.
Yeah, once I get everyone's email
Yeah.
addresses,
Once
then
you
I'll
get
copy
everything,
you in the
please do.
email.
Yeah. Okay. Great. Okay. So let's see. Any other organizational questions? No. Okay, then if not, I guess let's continue with data here. Okay. So say this was negatively associated as the mental score or score got higher, depression scores got lower. But say if you look at weight and waist size for the men health data, that's increasing. Unfortunately, looking at myself in the mirror, I can attest to that as well. Okay, so you get waist gets bigger, weight goes up. Okay, on the other hand, if we say look at the weight versus pulse, that's no association. Pulse changes a lot throughout the day depending on what you do, how nervous you are, etc. So it's not really associated with weight in any direct way. Okay. Important to realize, though, that association does not imply the causation. Okay. Just because two things are associated doesn't mean one causes the other. say you have pretty strong association, well, relatively good association here, but one is not, mental scores don't cause depression, and depression doesn't cause necessarily particular mental scores. We're just observation studies for a particular set of substance abusers. Okay. There is a classical example of two variables which are extremely strongly associated positively, but one doesn't cause the other. So if you look at the average prices of subway fare in New York City, just prices of subway fare, it stays the same for a few years generally in New York City, and average prices of pizza slice, that's what I was going to say. So average prices of pizza slice were actually almost the same throughout many, many years, from 1950 when it was 10 cents a piece to these days. We're quite close. So if you look at the graph, we're almost on a line. So there is a strong positive association. But needless to say, one is not causing the other, right? MTA officials do not check on pizza prices to set their ticket price. And pizza owners are also not really checking on MTA tickets prices to set the slice prices. It's just both prices have gone up due to kind of general, inflation and other forces which drive all the prices up for everything, right? So it's important also to realize the difference between observational studies and experiments. So all of these pictures we showed with scatter plots, this is so-called observational studies. We're just observing these people, okay? We're not doing any experiments on them. And generally, observational study cannot even be used, no matter how strong the relationship is. But they cannot be used, period, for any kind of cause and effect conclusions. It has to be an experiment, experimental study, like that study on cholesterol drug we mentioned in the beginning. That was experimental study. 200 volunteers were randomly broken into two groups. And then based on that, you can make some cause and effect conclusions, but not based on observational studies. To illustrate it a bit more, perhaps in somewhat funny way, let me mention this. So if you look at, say, number of people with sunburns coming, say, to emergency rooms, and consumption of ice cream from business data, they are strongly positively associated, but one is not causing the other. There is a big confounding variable, sun exposure, heat. That's what drives both things up. So one is not causing another. There is like a confounding or lurking variable. Whenever you do some kind of study, you try to account for such confounding variables in some explicit way. It's not easy always to have it kind of perfectly accounted for everything, but you try at least you try. So as far as sampling method, let's first introduce a little bit of terminology. Say, if you are studying, say, hourly wages of workers, so your ultimate goal is to describe the whole population of such workers, not a particular sample. And that would require a census, though, of all the workers, which is impractical, if not impossible, okay? So that's why in reality, instead you create a random sample. And these days, if it's sample well created, but even 12 to 1500 may be very much representative of the entire population you are studying, okay? But the key, of course, is that your random sample has to be representative of target population. And it's not an easy business. It's a very hard business of creating good representative sample. Good news, though, for you as students is that you're not going to be doing it. It's a task for more like upper level undergrads or even beginning grad school stats majors in big universities. They do it, but not an intra kind of business stat or general stat. They don't do such thing. Okay. So right, and also notice that another bit of terminology is that when you measure something on entire population, it's called parameter. Okay, so say if you're interested in average wages for the entire population of hourly workers, this average wage would be a parameter. But when you measure the same average wage for a sample, it has a different name. It's a statistic. Okay, and even notation is different. Say average mean for the whole population is a Greek letter, all the same mu for average mean. But average for a sample is the statistic is say X bar for the mean. So usually English, regular English letters are used with over bar, say, or above for the mean. Okay. So this kind of task of creating a representative sample failed dramatically, of course, many times. Most recently, it was perhaps the case of Trump election, right? So all the polling agencies predicted that Hillary gonna win, but in the end, they were all wrong. Trump won, and it was not a mathematical error. Math has worked out really well for many, many years for such polling techniques. It was not enough of representation of a population of voters, because many people, so-called Trump voters, were the ones which usually didn't even bother to vote. And they were not kind of assessed quite as much by polling agencies, but they came out in favor of Trump and gave him the victory. Okay. So there are many different sampling techniques. We are going to concentrate in our book, and in fact, more advanced courses also do the same, on so-called simple random sample. And such technique, a subset of individuals chosen randomly all have same probability. It's like a raffle, but computerized. And such a technique is kind of generally unbiased. You really don't want a biased sample. No amount of math and statistics can save your sample if it's biased. There's a rather dramatic example of very biased sample in early days of statistics when people still did not know quite what they were doing. So in 1936, Franklin Delano Roosevelt, FDR, was running for re-election against Alf Landon. And there was a popular journal at the time, Literary Digest magazine. I had sent out 10 million fake ballots to people they took like phone book directories, car ownership directories, and they sent out like 10 million fake ballots to see how people gonna vote. And based on such a huge sample, 2 million responded out of 10 million. Based on that, we predicted FDR is going to lose. On the other hand, George Gallup created a kind of scientifically randomized poll of only 50,000. And he predicted that FDR is going to win, and FDR won by a landslide. So how come the Literary Digest on such huge study was so wrong? Well, there are two reasons. One, they were very biased from the beginning, okay? So remember, they took people from phone directories and car ownership directories. But it's 1936, Great Depression, who had cars? People who were well off financially, they tend to be more conservative usually. So that was a terrible bias sample to start with. And to add insult to injury, or injury to insult, what's the right way to say it? I forgot. Was also very much so-called high non-response rate. Only 2 million out of 10 million actually bothered to respond. That's a voluntary sample like that with high non-response rate is not a good idea. That can create a lot of bias as well. So that's not a good way to collect data, and they were burned for it, you know. They suffered some financial losses after such wrong prediction, I believe. So it was really a disaster. Okay. Generally, self-selected polls of viewers are no good. Say, if you do self-selected poll of, say, viewers of Fox News, Fox is conservative. So it's not representative of entire population. And same with MSNBC, it's very liberal network. So you cannot trust their polls. It's biased to start with because it's just conservative or just liberals. Plus it's self-selected, kind of both problems which existed in this poll we mentioned in 1936. But I mean, people at, who publish these polls, they always say it's poll of our viewers. So they at least know better not to say that it's representative of the entire United States. But at least they kind of say that. Okay. There are many other sampling techniques, but don't worry too much about them. You don't need to know them for our class. There's so-called stratified sampling when population is divided into groups of similar cases like gender strata, men, women, social class, low, middle class, high. So when inside each strata, a simple random sample is taken. So say if a polling company trying to ensure that gender is equally represented in your poll, you may want to first break, on gender and then do equal size random samples in each gender. That's a reasonable approach, but because of stratification, it requires different techniques, so we will not run into it. So another approach to sampling is cluster sample. That's where population is divided into many groups similar to each other called clusters, but within cluster there's a lot of variability. That's different from stratification. Stratification, you have within each strata similar cases. But in cluster, you just maybe create geographical clusters. And then within each cluster, if it's small, you ask everybody. And if it's still too big, you do so-called multi-stage cluster. You create one simple random sample inside of each cluster. So say, this example of cluster sampling, say pre-election poll. Pollsters select, say, randomly 20 election precincts, and then survey everybody in this precinct, or if it's still too big, we may do random sample for multi-stage approach, and that would be kind of cluster sample. So again, we don't really use it in our course. Okay. So one more thing we need to discuss, and then we'll have a break. Let's talk just a bit more about statistical experiments. We've already kind of had some examples of it, but let's formalize it just a bit more. So when you talk about statistical experiments, it has to be kind of controlling cases assigned to different treatments, or just treatment and control, whatever it might be. And we try to control any other difference. Say in that new drug study we mentioned at the beginning of chapter, perhaps you want to ensure that patients takes the new drug and standard drug in similar manner, like after a meal with sufficient water, say, etc. Otherwise, you may get differences. Okay, so randomization has to be followed. So treatment groups assignment is random to account for variables that cannot be controlled. So randomizations helps to avoid things you cannot control, to avoid this lurking confounding variables as much as possible. So randomization really the key. replication. A sufficiently large sample must be collected to ensure the desired effect can at least be seen, hopefully, if it's there. So in fact, later chapter we derive exact sample sizes which need to be achieved to get certain margin of error. That's computed later, but that's sort of the idea. So there is also a kind of thoughtful way to deal with confounding variables called blocking. So confounding variable other than treatment, which is associated with explanatory and response variable. So in blocking approach, what we do, we first group individuals based on confounding variable into blocks, and then randomize cases within each block to treatment groups. So let's have an example of this. This may not be yet kind of so clearly spelled out. Let me get my writing pad. Where is it? Here. So let's describe what we would do perhaps in cholesterol study to kind of approach it better. Oops, jumped backwards somehow. Okay. So say we're looking at again our drug experiment for cholesterol. So it seems logical that the drug reaction could be perhaps different for people with moderately high cholesterol, say moderate, versus people with very high cholesterol, that's high group. So what you may want to do first is to create blocking variable, the level of cholesterol, two levels, moderate and high. And first you separate all 200 patients according to this variable. And then from inside of high level and moderate level cholesterol group, you take simple random sample of equal sizes. And that kind of ensures that you're taking care of low versus high cholesterol level. So in addition, by the way, whenever study is done, as much as possible, you try to make it so-called double blind. So if we're talking about this drug trials for a company to see if we want to invest in a full production, so double blinding would look like this. Neither doctor nor patient knows who is getting, say, new drug or a standard drug. Some third party is keeping track of it, okay? So if new drug is tested against no treatment, say you introduce placebo, like I said, to avoid placebo effect, because people who get even something which looks like drugs, sometimes they kind of talk themselves into feeling better. And you kind of want to avoid this kind of situations as much as possible. So let's just make a comment about the roadmap, and that will be the first chapter. Actually, it's relatively short, and we will take a break afterwards. So the general roadmap for the book is as follows. So first, the next chapter, we discuss descriptive statistics, like when you're trying to describe just the data file itself, not trying to infer anything about it. So things like mean, median, standard deviation, interquartile range, etc. So all of this is found based on just the file itself. So we only describe sample at hand, not trying to generalize, okay? So generalizing to population, that's the job of inferential statistics, okay? So when you're trying to infer from a sample mean, say, about true population mean, from a sample proportion to true population proportion. So it could be, say, so you found mean wages, say, for hourly workers for your sample is, let's say, 10.5. So based on the techniques which we learn later for inference, you would be able, say, to derive a confidence interval. So maybe it's from, let's say, 8 to, let's say, 13, of a range of 95% certainty true value is in that range. So that's sort of what you try to do with this late, okay? So you're trying to infer and yeah, so statistics, so we learned how to use sample data to make inferences about population parameters. But notice that that kind of approach requires basic knowledge of probability. So that's what we develop in the next two chapters, okay? And probability, well, not next two chapters, 3 and 4. Next one we study, of course, chapter 2, just descriptive. But after that, you have to delve for a bit into probability and probability distributions, because that's essential to understand the inferential statistics later, okay? So, yeah, and then in 5 through 7, you do the inferential statistics. And in chapter 8, we do basic correlation regression. And that's probably gonna be it time-wise. I'm not sure if we will have time for multiple and logistics. That's chapter 9, but we'll see. For now, the plan is at least to get through all the required stuff. Okay. Anyway, so any questions? No? Okay, then let's take, let's say 10 minutes break, come back and do a bit of chapter 2. Chapter 2 is quite a bit longer, so not planning to do all of it today probably, but maybe just a piece, we'll see, okay? So stop share and pause the recording, okay? So we're starting chapter 2, descriptive data analysis. And we're going to do numerical and categorical separately. And for numerical, the most standard way to compute the kind of central summary of the data is, of course, the average. So you take all this x1 through xn, say data points, you add them up and divide by how many you got. Notation is maybe looking a little scary, but it shouldn't be. This is just sum I1 to n of xi. All it means is just x1 plus x2 plus all the way to x7. You divide by n or multiply by 1 over n. So if the numbers are this, 1, 2, 2, 4, 5, and 10, you add them up to 24. And there are 6 of them, divide by 6. And that's 4. So, but that's very small data set. In reality, you need R or some other statistical software to compute these things. But let's start with a small example first. So once you load R on your computers, you'll start RStudio and you'll see something like this, but not this exact thing. So you need to get to the file. So how do you get to the file? So you, looks like we made actually this class, our class made official, I think. That's good news. Okay. So I guess the question is when you're gonna get CRNs. I should, once I get CRN, I'll send Jenny, I guess, or all of you if I got everybody's email and you register. Okay. So anyway, let's get back here. Okay. So see this myr files directory. Okay. So you download either all of them, probably better not to download all of them at once. I might update things as we go. So for now, just download chapter 2 descriptive, this one, chapter 2 descriptive.r. Okay. So download it into some directory where you can find it later. And then in the RStudio, you go File, Open File, and chapter 2 descriptive. You click on it and it gets you this file. Okay. And this is exactly the first thing we do. So to put this 1, 2, 2, 4, 5, and 10 is so that R knows that you have to do X equal C parentheses when you just give the numbers with commas and close parentheses. These things here, green with number sign in front, are so-called comments. This is for us humans to understand what's going on. Computer just ignores this comment. So you said X equals C parentheses, and in parentheses you put all these numbers. And when the command is mean, so mean X, I set X bar equal to mean X, and I print X bar. If I just run this, it will only compute it, but will not tell me what it is. So I put semicolon X bar to actually display it. So all you do when you select what you want and click this run button, boom, and it's done. It's 4, surprise, surprise, down here, okay? So by the way, we can look at this computation step by step as well. We don't have to, but we can. So I can use sum command to find the sum of x's. That's this line, select run 24. N is length of x. That's gonna give me 6. Length, how many elements in this array of numbers. And then x bar is just the ratio of sum to the n. And of course, it's back to 4. Okay. So, but that's not super impressive because this is a small data set, although these commands will be very useful, say, on exam. Because on exam, I'm not going to give you a huge file, rather, I'm going to give you just a set of numbers. You enter them like this. Leah, did you have a question? I saw your hand.
Yeah, I was just confused. What does X bar mean?
X bar is just the name I gave it. I can call it anything, but I called it X bar because that's the notation which we used in the definition, right?
Got it. So basically, X is just the
yeah.
variable you're giving for the data set. X bar is
right. X bar is just the name I gave it. You can call it X2 or X7. You know, it will compute just the same. Okay. So, but that again was not terribly impressive. What would be more impressive is to actually get it on a file. So that requires just a little bit extra work. So this mosaic data is a separate package, and R uses many, like thousands and thousands special packages. But specifically to get this mosaic data, you would have to go into a file and remove this number sign to make this line install packages mosaic data. That would have to be made not a comment. And you would select it and click run. I'm not going to do it because on my computer, of course, it's already installed. But first time around, you have to do it only once. You never have to do it again. Okay. So I'm making it a comment again. So once it's installed, each time you start R, you have to load that library. So you run library mosaic data, and it doesn't produce any errors. If you see like red, in red color, some stuff like this, that's some kind of errors or warnings. I don't get any of those. You shouldn't if everything runs. Okay. So it loads the bunch of data files, in particular that help RCT file for substance abusers. So that question mark file name will give you description of a file. There are lots of different variables, age, depression score. I only included a few in what I showed you. This has a lot of variables. Okay, it's a bigger file. And say for the data file for the wages for hourly workers, CPS 85, so this is more like business and economics. If you run that, it gives you a description of that for our wages, education level, race. There are a bit less variables here, but also not a small file. There are 534 people in this file. See, data frame with that many observations. And if I say want to know mean, of these wages. See how I do it? CPS 85, name of a file, and then $sign and variable of interest wage. So if I run that, tells me that there is average wages, $9 approximately. And if I do it mean help RCT CSD, that's average depression score for the substance abusers. Okay, so really this mean command works the same. You just have to give it a proper column of a file. Say for wages, for business kind of data, it's mean CPS 85 $sign wage. Whatever is name of a file, then $sign to identify a particular variable, and you give a name of variable. Okay. So that's how it works, kind of rather convenient. Yes, so I'm describing this here. So notice that CSD depression scores, that's a sample, that's for a sample from a population of such depression scores of all substance abusers. So this was a sample mean here. You can also talk about population mean. It's defined really the same way. It's just a Greek letter to signify population mean, say of all depression scores or all the wages. It's still adding up all the wages over N, except it's capital N, total number of all the hourly workers, say, which for many millions, I would assume. Okay. So most of the time it's impractical or impossible to compute the mean of entire population. So that's when you do the sample mean, it's called point estimate. And we are hoping that it represents the true population mean with some accuracy. What's accuracy? That requires chapters 5 and 7. That's late, but at least it's an estimate. So 902 is a point estimate of the true population mean of hourly wages for all kind of similar hourly workers. Okay. So in chapter 7, we develop tools to characterize such means in more detail, find confidence interval, do hypothesis testing for such means. Okay. But you should think of question. Yes, question.
Why are you saying it's impossible to compute the mean?
Well, you would have to then collect all these millions of hourly workers.
You mean the entire population as opposed to
For
the
entire
sample?
population, yeah. For a sample,
okay.
of course it's possible. It's very possible. We just done it, yeah. For entire population, that's impractical or impossible, yeah. But for sample, that's exactly what you do. You have to be a bit careful with averages or means like this. Here is a possible kind of wrong computation. So let's say you are given average incomes for all 50 states. And one might say, why don't we take these averages, add them up and divide by 50 and get average for entire United States? But that would not be correct, because the states have very, very different populations. California is many, many times more than, say, North Dakota population, probably like 1,000 or at least 100 times more, okay? So you cannot do it like this. You have to either do like start from scratch, collect all these people and do the census and find all their incomes and do average income from scratch. There is a way around it with so-called weighted means, but it's not terribly relevant for our statistics course, so we're not going to pursue it. But there is, as far as a kind of economics problem of finding average income, if you know average incomes for 50 states, if you know population in each state, you can actually do so-called weighted mean. That's a possibility, but not so interesting for us. So here's an interesting problem, actually, using the means. Okay, so let's do slightly different ones than already done here to kind of show you some different examples as well. So let's say you have a sample, say, of 200 workers in mind, okay? And you started collecting data, and you were able to get the data for 199 of them. One you couldn't track, say, on a particular day. And you compute the mean based on this 199 workers, say hourly workers, and you found that the average is, say, 10.5, okay? And then finally you were able to track this last guy, and his, say, hourly wage is, let's say, $13.5 per hour. So do you have to recompute the whole thing, or there is like a way to use the previous mean to actually find the new mean? Turns out there is a slightly clever way to do it. You proceed in the following way. So let's go back to 199 workers we started with. So what's the mean? It's a sum of all of this x1 plus x2 all the way to x199 over 199, right? And we know it's 10.5, right? So we can actually find the sum from 1 to 199 workers is a product of 199 times 10.5. Let me clean this up a bit. I have to move my pad a little bit so that handwriting a bit better. So you have 199 here. You have 10.5. So you can find when the sum of x1 plus x2 all the way to x199 is a product of 199 times 10.5. So that we put into calculator, or R, doesn't matter, I guess. So you would have 199 here, actually. So 199 times 10.5. So that is 2089.5, okay? So then, how can we add the last one, the 200 guy who got the test, 13.5? Well, the new mean is a sum of all of this, including this guy, but we have sum of first 199 of them. So it's 289.5 plus 13.5 divided by 200 now. See, that was a bit clever, but that's one of the problems in homework. So I wanted to show you that. So then we have 20, 89.5. You add 13.5 and divide this whole thing by 200. And notice, by the way, we got a number slightly larger than previous mean, which is not surprising because his score, his wage was a little bit higher than the previous mean. So no wonder he dragged the mean a little bit up. Okay. So any questions? So it's also quite important to talk about the shape of the data. And that could be done with so-called histogram. It's a graphical representation of numerical data by grouping observation into the bins. So then you just create the bins, and in each bin you count how many got into that particular bin. I've seen some books and some professors who are so cruel that they make students to do it by hand. I think it's cruel and unusual punishment, which should be punished by under American Constitution. That's what computers are for. And all you have to do in R is a hist command. on a proper variable. Say when you run hist of CPS $85 wage, that's your diagram here for the wages. It has kind of characteristic shape, which is so-called skewed right. We'll define it in a second. Wages, incomes, they all tend to be skewed right quite a bit because few people make more and the bulk not so much. Okay. Notice you can regulate how many breaks you make. Say there was this basic graph which produced automatically, which is actually pretty good already. But you can force breaks equal to 20, say, and that produces somewhat more detailed histogram. But you don't want to have too many breaks either. When graph kind of breaks down into individual spikes, that's not very good either. This is perhaps optimal, maybe what we see here, but this one is not bad as well. Okay, so y-axis here counts the frequency. See, it says frequency. Okay, but oftentimes it's better to use so-called relative frequencies, percentages out of the total. Then it's easier to compare perhaps to different distributions. So all what changes is that I have to add comma prob true. Prob true will force probabilities on y-axis. See, we used to have actual counts. Now with the probabilities out of the total. Density kind of showing you density. So histograms show kind of data density. Higher bars represent where data are more common and lower bars where it's less common. Say most hourly workers are making actually like less than $10 per hour. This is probably a bit older data, not recent. You know, minimal wages have gone up. This is probably from 80s, 90s. My first job back at University of Michigan was like looking at some probes and microscope, and that paid $5 an hour in the shift. Okay, but it was a job. Okay. So yeah, so most offers making well below, most workers making well below $10 an hour. Few make $20 an hour, and there is one kind of outlier, so-called, which makes like almost $50 an hour, $45 an hour. Now the shape we're observing here is so-called skewed right. That's mostly data, most of the data on the left, and there is like a long right tail. This is right skewed shape. Okay, so income is always very much skewed right. This is income distribution in 2014. So most of the people don't make too much, but there are a few who make a lot, and they create this kind of thin right tail. Okay, but if you look, say, at the histogram of physical condition score in help RCT file, like this, help RCT, $PCS, physical score, that's skewed left on the other hand. So most people are in this scores and few are in a much worse shape, I guess. So, but it's skewed left, okay? So that's a left skewed shape. But if we say consider this data set, M health, and do histogram of heights, tends to be so-called symmetric, not skewed left or right. But there is something extra I had to do here. What's that? So M health data file is not part of any library I know of. I just have it from some other course I taught before. So I had to load. It's not a big file. It's mhealth.csv. So how to get to run something like this in R? So, so this, by the way, shows what we have been working on. So this is this histogram, this histogram. You can even get the density plot like this with plot density. Density basically is just smoothed out histogram curve. That's all it is really. And PCS scores skewed left. All right. Now, there is a command read CSV. mhealth.csv and string as factors. This basically you copy, paste if you need some other file. In my file, it's already available. For a couple of things you need to do to make it run like that. First of all, in addition to downloading chapter 2 descriptive from my files, you also download this mhelp.csv and put it in the same directory where your R files are going to be. Make a separate directory for R files. And mhelp CSV should go into the same exact directory so that it knows where to look for it. But still, if you run it, it will probably produce an error. Why? Because it also needs to be told to look for it in that same directory. So in order to do this, you go to Session, Set Working Directory, and to Source File Location. So let me actually put this here as a comment. So you click on Session, and that's on the top. Then you choose, once in Session, you choose Set Working Directory. Set Working Directory. And in there, you choose to source file location. So then it should be able to run it. So when I run it, it doesn't give me any errors. If you see errors, it means that either you haven't downloaded in the right place, or you forgot session, set working directory steps. Generally, with computers, doing anything on a computer, it's very easy to get stuck. So I would strongly recommend for you to get R going. And obviously, next time we can also spend a lot of time trying to make sure that your R works. But don't even wait for the next time. Email me once your R is set up and you try and you got stuck on something. If you got stuck on something, email me. We will create individualized Zoom session. You can share a screen and I'll see and help you to get unstuck, okay? As far as tutoring, you can probably get tutoring in your department for general statistics, but I'm pretty sure nobody knows R except me. Not that I'm that special, but Tura is not very computational, So I'm only one, I think, in the whole building on Avenue J who knows R. And I'm not sure what about LCW. I suspect the same thing. I know some good guys who do advanced stuff in computer science with data on Python. Python is like a whole programming language, but they approach things differently from the point of view of computer science, of course, being computer science professors. And their students are doing Python programming all the time, so it doesn't make sense to teach them R. They do everything in Python. Python is a great programming language, but it's a bit harder to use, and it's not just for statistics. This is just for statistics. Although you can do some general programming stuff as well in R, but it's really statistics back. Anyway, so it loaded and I click hist and I get pretty symmetric histogram of heights. So heights tend to be pretty symmetric, so-called bell shape. We'll talk more about bell shape later, but it's always symmetric, okay? Now, based also on the shape of a graph, we identify something called a mode. So the mode is simply a prominent peak in the distribution. The data doesn't have to have a mode. Say when it's pretty uniform like this histogram, then it just doesn't have a mode. The data could be unimodal. It could be bimodal if there are two clear maxima. Say sales could look like unimodal, but could also be bimodal with two maxima corresponding to like two different, say, stores or two different something. Could be even multi-modal, several different modes. But mode is not something you can compute so much on R. It's more like just assessing which data points appear a lot, or graph is a good way to see the mode. Okay. So let's see, let's talk at least a bit about variance and standard deviation and maybe call it a day. It's already kind of almost 2 hours. So a lot of interest is given not only to the central measure of the data, which the mean or average is, and later also we'll learn about median. It's also another different measure of the center, but also the variance, so-called, and standard deviation, which describe the spread of the data. Okay. In fact, for stock market, volatility of the stock is a very, very important measure. It tells you how dangerous it is to invest in that stock, right? So standard deviation is a common way to measure actually the market volatility, and there is another measure, coefficient of variation, we'll mention as well. It's also used a lot for stocks. Now, one more thing perhaps worth mentioning is that range is also kind of used as a measure of spread, but it's not a good measure. Range is simply the difference, highest minus the lowest. Standard deviation a lot more subtle. It really tries to take into account deviations from the mean, as we will see. But I should probably mention at least the range, like at least it gives you mean and max, like say stock prices over the year. What was the lowest stock price and what was highest stock price? It doesn't quite show you how spread out the whole data is, but at least it gives you the most extreme ones. So that could be useful to know. Okay. So let's go back to our small data set first to understand how to approach variance and standard deviation. So first of all, we're going to say like what deviation from what, first of all. Well, we're going to look at deviations from the mean, okay? So therefore, it makes sense to define these deviations as the differences, the actual data minus the mean. So those are going to be deviations. But the mean is in the middle of the data. So first idea might be, why don't we compute these deviations and just average them? That's a bad idea, because mean is in the middle of the data. So some values are going to be above the mean, so you get positive deviations. Another data is going to be below the mean, so you get negative deviation. And if you start adding them up to find the average, they're going to cancel each other out. In fact, you can show mathematically exactly that they always cancel out to 0. Okay? So not a good idea. So what to do? So it's been shown in math courses that the better idea is to average out squares of the deviation. Squares will remove the plus, the minuses. Negative squared is positive. And we're going to try to sort of average the deviations, square deviations from the mean. So to illustrate it, you don't need to do it to compute anything. Very important. So this is just for illustration purposes, this code. So I again put x as C parenthesis, all the data. I set x bar to be mean of this x's, just like we did before. The deviations we said is x's minus the mean. So I do x minus x bar. That gives me all the deviations. And D2 is going to be square of all this deviation. And it's convenient to bind them together as columns. The command is cbind to bind columns, C for column. And I bind together the x's. The mean x bar is repeated as many times as there are data. So D are the differences. Well, 1 minus 4 is -3, 2 minus 4, -2, 4 minus 4, 0, 10 minus 4, 6. And notice, by the way, if you add up these differences, you have -5, -7, plus 7, it's 0, just like I promised the deviations themselves, always add up to 0, okay? But if you square them, you get set of positive numbers. So what we propose to do is, may look something strange, but just bear with me with this definition, what we're doing. So we're telling to take the sums of deviations squared. So add up the squared deviation. So 1 minus 4 minus 3 squared 9 minus 2 squared 4, 6 squared 56. So add them all up. To average them, we would divide by n. For some rather subtle mathematical reason, it's divided by n minus 1. We will talk about this in a second, but it's at least sort of averaging, right? Real average would be if you divide by n, sort of averaging if you divide by n minus 1. And why square root? Square root because we started with original units. Say if this is stock prices in dollars, then when you square it, you got dollars squared, but dollars squared don't make too much sense. So when you do square root of this average, you get back to dollars. And that's what you want, really. You want the measure of spread in the same dollar units as the original stock prices, right? So that's what you get, okay? So if you actually plug in, you have 9 plus 4, etc., 36 over 5 square roots, so you get 329. Needless to say, you are not going to be computing like this. So just for the sake of it, I put a formula in R, which does the square root, sum of the square deviations over n minus 1, but that's not how you compute it. All you have to do in R is to type SD of x. SD stands for standard deviation, and it finds it right away. R is great this way. It has commands for everything, you know. So that's sort of what you obtain here, okay? And so standard deviation is what we're going to use all the time. There's also something called variance, which we're not going to use in our course quite as much. But you should know the term because it's used as well. So all variance is just a square of standard deviation. So it will just remove the square root. That's really all that is. Why define something which is square of what you already know? Well, the answer is, again, somewhat mathematical. And when you do probability, more detailed advanced probability, it's oftentimes easier to compute things without square roots. So you deal with variances and then take square root later for standard deviation. Statistics, you do just the opposite. You deal with standard deviations and only occasionally mention variance. But you just have to know the term, okay? So why did we divide by n minus 1 instead of n? The reason, as I said, somewhat subtle. Nobody ever is going to ask you, well, I shouldn't say nobody ever. If you study more advanced math, you will run into this. But for this course, I will never ask you why it's n minus 1 and not n. So I'm just giving this explanation as FYI. And you will not get such a question in homework, not on exam, of course, no way, okay? But the idea, just the wording called degree of freedom is quite important. So at least the idea, just to give you ideas, that in the definition of standard deviation, we're using already x bar. We're using already parameter from the previous estimate. And that kind of limits how many of the x's can change freely. In fact, it's only n minus 1, because if you change all of them, your x bar will change. It's different, going to be different x bar. So this degree of freedom, n minus 1, is this measure of how many variables can change free. I'm sure it doesn't sound very clear, I'm afraid, and not sure how to make it a lot more clear. The reason somewhat mathematical. Moreover, in more advanced probability, it's shown that if you define the population standard deviation of Greek letter sigma as a similar kind of sum. This is population variance as xi minus mu, though not x bar, but true population mean mu squared. You sum and divide by total n. Here you don't have to do n minus 1. Then if you have here n minus 1, then this is a good unbiased estimator of a true population standard, of true population variance. And if you had here n, you will be biased. And who wants to be biased? Nobody wants to be biased. So we use n minus 1. So again, this is somewhat subtle points. Nobody ever is going to ask you about this in exam. No way. And of course, R can deal with files. So help RCT has 453 patients. Good luck even imagining to compute standard deviation by hand for that. Imagine this computation done on 453 people. You'll kill yourself, okay? So instead you just type SD, help RCT CSD, and it gives you the standard deviation. And var command gives you variance if you want variance, although this is just square of that. So for wages, SD of 534, I think, workers in that file found that 5.13 is the standard deviations of workers' wages, and variance is square of that, okay? So a good question might immediately kind of present itself. Okay, we found standard deviation, it's a number. You told us it's a measure of spread, but what does it really give you? It's just a number. How much spread then if you know this number? So we know, say, average for wages is like about $9, and this is 515 a standard deviation. All right, so what does it tell us really? Well, to tell you the significance of standard deviation, we're going to look at two results. This is proved in detail in chapter 4, and something else we'll also mention proved in math courses, but that explains you why standard deviation is useful. So in chapter 4, we're going to prove that if your data is bell-shaped, and many things are bell-shaped, not wages though, but heights, and some measurements, many measurements are bell-shaped. So for bell-shaped data, if you go from the sample mean plus minus 1 standard deviation, you're guaranteed to have 68% of data inside. And if you go 2 standard deviations away from the mean, the most common, you get 95%. Most of the data is inside of plus minus 2 standard deviations for the bell shape. And if you go 3 standard deviations, almost everybody really is inside. So a good example of this might be IQ scores. IQ scores tend to be bell-shaped, with mean 100 and standard deviation 15. So if you go mean 100 plus minus 1 times 15, 1 standard deviation from 85 to 115, that's 68% of all data. If you go mean plus minus 2 standard deviations, 2 times 15, 30, so that's between 70 and 130. So 95% of people have IQ scores from 70 to 130. In fact, METSA Society, that's Society for People of Higher IQs, that starts with 132, I believe. And 3 standard deviations, 100 plus minus 3 times 15, that's 45, that's from 55 to 145. So people above 145 are really rare, some really special people. So 99.7% of all people have IQ in this range. Only really special ones are more than 145. But we've seen that many distributions are not many, but quite a few are not bell-shaped. Specifically, income is not bell-shaped. So to understand what standard deviation tells you for a distribution which is skewed to the right, like income, we have to use the result from probability called Chebyshev theorem, okay? So Chebyshev theorem tells that the minimum proportion, meaning at least that much, maybe more, but at least minimum guaranteed proportion of observations within k standard deviation of a mean is 1 minus 1 over k squared. So say if we take specifically k equal 2 plus minus 2 standard deviations of a mean, 2 squared is 4, and 1 minus 1/4 is 3/4. So even for the very highly skewed income data, we're guaranteed with at least 3/4 of the data within plus minus 2 standard deviation. Okay. So that's what we have. But don't be too carried away with just this means and standard deviation. Do not skip looking at the histogram. It's absolutely essential. In fact, this is a classic example. Someone derived the specific histograms from actually like mathematical formulas. It turns out that these 3 histograms have exactly the same mean, 0, and exactly same standard deviation, 1. But clearly they are very, very, very different. So having mean and standard deviation is never a replacement for looking at histogram. When you got data, take a look at the histogram. Always do. Okay. So let's see. Should we stop here? It's like 2 hours. Ladies, feel like it's enough for today? Yes, no? What do you think? So just a sec, let's do just a bit more, okay? It's actually an interesting idea which has huge application in stock market. So we mentioned before that standard deviation is in the same units as the original units of variables. Say if we're talking about stock market measurements of a particular stock, say in dollars, then standard deviation will also be in dollars, and that's good. It's the way it should be. Nothing wrong with that. But think about this way. Let's say the same exact stock is also listed, say, on Japanese stock exchange. And $1 is quite a few yens. I don't remember exact currency change, but it's a lot of yens, $1. So if you recompute the mean and standard deviation suddenly becomes quite a bit bigger, and mean also becomes quite a bit bigger. But did it really become more volatile? No, it's the same exact stock. It's just different currency, bigger numbers. So to account for things like that, people introduce coefficient of variation, CV. It's you take standard deviation, you divide it by X bar. That's the sample mean. That way you get non-dimensional number, and you multiply it by 100%. Okay. So then if you have coefficient of variation, which is only a few percent, then it's a very stable stock, kind of good to invest, perhaps not so dangerous. On the other hand, if it's getting close to 100% or even can be more than 100 in principle, if S is greater than X bar, not often, but could be, that's a highly volatile stock. That's very dangerous investment. There's very wide swings in prices of this stuff. So to illustrate it, I have a data here on 2 stocks from company A and B, here and here. And we go through the computation of CV step by step. Notice, like no magic, I call it A bar, mean of stock A. That's 232 approximate. SD, standard deviation of stock A. That's SA, we're gonna call it, it's 152. And you take this SA, 152 approximately, divide by A bar 231, multiply by 100. So coefficient of variation for stock A, for company A is 65.5. That's pretty volatile, fairly high volatility, high coefficient of variation. So let's look at this stock. So mean is 172.6, SD 7.1. You divide 7.1 by 172 and multiply by 100, you get only 4.1%. So this is a very, very stable stock. Okay. So let's see, should we do just a bit more here for medians and stuff? Well, let's not overload the first day. Let's first day be a little bit easier. Okay, sounds good. Okay, now